There's a couple different ways you could do this first one because, guys, you're going to have to be using like 3 different of the exponent rules that we learned yesterday. So, first of all, like there's division, right? So you subtract those exponent, but there's also like this out here has to get applied to everything. So maybe you did that first. How many of you did do that first? Applied that 3 to everything, okay? Did anybody do the division rule first? You could do that first. I usually simplify inside the parentheses, so we could go ahead and do that first if we want to. If we do, I'm just going to leave the 6 alone for a second. So x to the 2 minus 4, you do. That's negative 2. And then y to the 4 minus 2. Remember, you always write it in the numerator when you use that rule. So right now it's kind of like this, okay? But the x to the negative second, we're going to use the rule where we flip it. So that's actually going to end up coming down to the denominator, so you can make it x to the positive second, okay? Now, all I did was work inside the parentheses so far. This 3 is still out here. We're kind of think of it in layers, like PEMDAS, essentially, like we did what was in the parentheses first, okay? Now, again, you don't have to do that. You could have raised everything in here to the 3rd power as your first step, but then you're going to have to subtract the exponents afterwards. So you have to do both rules no matter which order you do it in. So now if I raise, you might want to put a 1 here. If I raise everything to the power of 3, that's 6 to the 1 times 3, and then y to the 2 times 3, and x to the 2 times 3. So then it ends up being 6 to the power of 3. We want to actually evaluate that. That's 216 y to the 6 over x to the 6. So again, you may have done it in a different order than me, but you still should get the same answer. Next question is, even if you don't know without like what the graph of this is, like if it's not familiar to you, you have choices. So like go plug the choices in your calculator. Hopefully you know this one's a line before you even put it in your calculator. Like that's a linear equation. I hope you know, because we just devoted a whole chapter to it, that this would make a parabola if we graph it. These ones you're probably not as familiar with. So just graph them in your calculator and see what they look like, and you would see that this one would match this graph, okay? Now, just to give you a heads up, later in the year, we'll study the shapes of this graph and this type of graph. And then the parent function, if you remember, just means like you can make transformations to this. Like if I add 3, what it would do is it would shift the graph up 3, for example, okay? So like if you graph this in your calculator, it's actually going to look like this. So the graph that's shown in this picture is just like it's actually this. It is the thing shifted to the left 2 units, okay? But the parent function would just look like this if you graphed it. We'll talk about that later in the year, but any graph that you ever graph, like we did it with parabolas, you can shift them up and down and left and right. You can stretch them, you can shrink them, okay? All right, so we're getting into 2.2 today. We're going to learn about polynomials, and we're going to learn about something called synthetic substitution. So right now, just put your pencil down for a minute. I just want you to listen. You have seen some examples of polynomials before in your study of math, whether you remember this fancy word or not. This thing right here is an example of a polynomial. It would make a line if we graph it. This thing is an example of a polynomial. Hopefully you know, because again, we just devoted a whole chapter to it, that it would make a parabola if we graph it when it has an exponent of 2, okay? So polynomials, though, just some background information, they can have, like if I had just this with nothing else, that's called a monomial when it only has one term. We actually had that in an earlier chapter, okay? Once it has 2 terms, it's called a binomial. So a polynomial can have just one term, or it can have like many terms, okay? Like as many as you want, pretty much. So the thing is, that means that like if you look at all the separate terms, The ones that we studied so far have had an exponent of 1 or an exponent of 2. And again, when it has an exponent of 1, it makes a linear shape. Exponent of 2 makes a parabola. If it has an exponent of 5 or 4 or 7, or that's what polynomials are. Like sometimes that exponent won't just be a 2 or a 1. It could be higher. Then you'll see that those make a certain type of shape, okay? So I wanted to give you just a few examples with numbers first, because we're about to take some definition notes. And the definition, just listen again for a second. I'll tell you what to write. In the definition, it looks like this. It gets a little confusing because there's like all these variables in it, okay? But I want you to imagine it instead with like numbers: 4x to the 5th, 7x to the 3rd, negative 9x, okay? So it's just that you can have lots of different terms. Like I could have even more than just 4 like this has, okay? So what you're going to want to write first is that a polynomial is either a monomial. Again, mono means it would only have one term. Like here's an example of something that's a monomial, okay? As soon as it becomes a sum of monomials, so like it has more than one term in it, so it could be, that's called a binomial if it has 2 terms. It could be a trinomial, okay? Or it could have even more terms than that, because if this exponent is something higher like a 5, then it could have like 5 terms in it then, okay? But a monomial is what we specifically call it if it only has 1 term in it. Okay, you may remember if it has 2 terms, it's a binomial. If it has 3, it's a trinomial. But all of those things, even if it had 50 terms in it, it's still called a polynomial. Whether it has 1 term or 50 terms, it's called a polynomial, okay? So like a monomial is still a polynomial. A binomial is still a polynomial. If it had 50 terms, it's a polynomial, okay? So a polynomial is a function of this format. So again, maybe it just has 1 term, maybe it has many terms. But what's important is that if you look at the structure of this, do you see how the exponent, the n there, to see how the next one goes n minus 1? Like look at my example. This exponent was 2. 2 minus 1. The next exponent is 1, and so on. Like usually we write it so that the exponents go in order from greatest to least. So if you had a polynomial function that looked like 5x to the 5th plus 6x to the 4th plus 2x to the 3rd, like see how the exponents are going down by 1 each time as I'm writing it? That's what this is trying to say to you. It's just we write it in an order so that the exponents go down by 1 each time. You start with whichever term has the highest and then it goes down. So to be a polynomial, though, this is really important, this exponent has to be a whole number. So like if it were a decimal exponent, that's not a polynomial. Or if the exponent was a negative number, it's not a polynomial, because literally the definition of a polynomial says that n, the exponent, has to be a whole number. Okay. Okay. So continuing with that same thing, a sub n is what we call the leading coefficient. So again, guys, I want to give you an example here off to the side with numbers, because it just makes it a little easier to understand if we have numbers instead of all of these variables. So if you had an example that looked like this, the degree of that, or I'm sorry, let's do leading coefficient first. The leading coefficient would be this number here. Like all of these are called coefficients, but the leading one, the one that comes first, is 5. So that would be the leading coefficient in that example, okay? So it's basically it's the coefficient on the term that has the highest degree, okay? And by the way, I just used the word degree. I shouldn't probably do that till we've defined it yet. The degree in this case is 3 in this example. Basically, it's the highest exponent. Like you might want to add that. It's the highest exponent that you see. Because remember I told you, like, if this is 5, the next one is 5 minus 1, so 4, okay? So that's why we say that it's n. It's always the highest one. And then the constant term is that number on the end, the part that has no variable with it. So in my example, the constant would be the number 1. It's the part that has no variable with it, okay? Now, when you look at the degree of the polynomial, like again, my example here, we say that it has degree 3 because that's the highest exponent that you see there. You name a polynomial based on the degree. So on this next slide, you're not going to have to write this down because it's on your formula sheet that I gave you yesterday. So you might want to get that formula sheet out in front of you. So if you have a polynomial that has a degree of 2, we already know because we spent all of chapter 1 on it, it's called a quadratic equation. If you have a polynomial that has degree 1, like here's an example, that's a linear equation. Okay, these words are probably new to you. If you have a polynomial of degree 3, meaning the highest exponent is 3, it's called a cubic function. If the highest exponent is 4, it's called a quartic function, okay? So just like you'll learn next week when we're going to graph some of these ones that have exponents of 3 and 4. So they kind of have a certain shape to them, just like every quadratic makes a parabola and every linear makes a line. If it's cubic, it's going to kind of have a certain shape to it. If it's quartic, it's going to have a certain shape to it, okay? One more thing you need to write down in your notes here. This definition at the bottom, a polynomial is in standard form when its term of highest degree comes first, then the second highest, and so on. Like if you look at this right here, it's a good example of something that's in standard form because see how it has the term that has an exponent of 3 first, then 2, then 1. Okay, standard form says take the term that has the highest degree and write it first, the highest exponent, then the next lowest, then so on. You're basically writing it in order from greatest to least exponent, okay? It's important to know how to write something in standard form because those definitions that we had on the last slide, like leading coefficient, for example, you don't want to try to figure out what the leading coefficient is until you have the polynomial written in standard form, okay? So standard form is like super important. So as you're finishing writing that definition, on the next slide, we're going to practice all of this vocabulary that we just learned. Like, first of all, just knowing if something is a polynomial. Second of all, being able to know the degree of it. Being able to know, is it linear or is it quartic or is it quadratic? Okay, that has to do with the degree. Does everybody have this definition down? Okay, so let's look at an example. Decide, you can write this polynomial down in your notes. We're going to decide whether it's well, I should say write the function down. We're going to decide if it's a polynomial. And if it is, we're going to write it in standard form, tell the degree, type, and leading coefficient. So how are we going to know if it's a polynomial? Basically, you have to look at all the exponents. Remember our definition earlier said the exponents have to be whole numbers. So we have a 4, we have a 2, and then this part is technically, you could think of it like x to the 0 when there's nothing written, because remember how yesterday we learned anything to the 0 power is 1? So that's why we never really write that, because 3 times 1 would just be 3, right? but we're good because the exponents are all whole numbers. Even if we did have x to the 0, 0 is still a whole number, okay? So determine whether it's a polynomial. Yes, it is. So we're going to go on. We're going to write it in standard form. This one's actually in standard form already because the highest exponent is 4, and it comes first, and then 2, and then, again, this part is called the constant that doesn't have a variable next to it. You're always going to write that last, okay? So it's already in standard form. The exponents already go greatest to least. So the degree is going to be the highest exponent, 4, and the leading coefficient is going to be the coefficient on the term that has the highest exponent. So it's a 1. Like -1/4 is also a coefficient, but 1 is the leading coefficient, okay? And then what else? We have to state the type. So the type has to do with the degree. So look back at your table for this. If it has a degree of 4, we call it a quartic function. Okay? We're going to do another one together so you get the hang of it. First, we're supposed to just figure out, is the function a polynomial function? So again, look through it every term. Like this has got 3 terms in it. The first one, the x has an exponent of 1 when there's no exponent written there. The second term is actually what we call the constant because there's no variable. See how it has no x? It's kind of like x to the 0 if you want to think of it like that. And then this one has exponent of 2, but we're good because all the exponents are whole numbers. So it is a polynomial function. So if we want to write it in standard form, we have to write the term that has the highest exponent first. That would be this one. So our pi x squared is going to come first. Then we go from greatest to least. So that means this term's going to come next. So since it's positive, we write plus 7x to the first. I don't really need to put the exponent anymore. And then the constant, so negative radical 3 is going to come last. Okay? The degree is 2. That's the highest exponent. Let's do type next, because the way that you figure out the type is by looking at the degree. This one you really should know without looking back at your table, because again, we just did a whole chapter about when the degree is 2, it's a quadratic function. Like this would make a parabola if we graphed it. Okay, and then the leading coefficient, I'm going to abbreviate that instead of writing out the words leading coefficient. Remember, don't try to tell me it's 7 because you have to put, it has to be the coefficient that comes first after you put them in the right order. So it's pi, okay? Like it has to be written in standard form before you try to figure out which one is the leading coefficient. Because like all of these things are coefficients, but the one that comes first when they're in standard form is called the leader, the leading coefficient, okay? Let's do another slide. Copy this one down into your notes. Same question. We got to figure out first, is it a polynomial function? And this one is not, because here's the red flag. X to the negative first. You can't remember the definition said the exponents have to be whole numbers. So this one is not a polynomial function. It's a different type of function that you'll learn about later in the year when it's got a negative exponent like that. Okay, look through your exponents on the next one. We have a 1, we have a 5, but this is a problem right here. The definition we wrote down earlier said the exponents have to be whole numbers. So you can't have a variable as an exponent because it has to be a whole number. It can't be a variable. So this is another one that's not a polynomial function. Again, it's some other type of function that you'll learn about later. So I'm going to give you the chance to try a couple on your own. You take a look at this first one, and we're going to answer the same question. First of all, is it a polynomial? Right? Whether you think it is or not. And then if it is, go on and answer the questions. Tell me the degree, type, and leading coefficient. So again, a constant is like if there were an x to the 0, because x to the 0 is 1, we don't write that, right? Because anything to the 0 is 1. But we're good, though, because a 0 counts. It's a whole number, and then 1. So all the exponents are whole numbers. So it is a polynomial. We'll say yes. Standard form, the term with the highest exponent, which is just a 1, has to come first, so negative 2x, and then the positive 13. 13, remember, is called the constant. You're always going to write the constant last, okay, the part that has no variable. So the degree, again, is the highest exponent that there is, which is just 1, which means the type, it's a linear function. Like if we graph this, it's going to make a line. How do I know that? Look to the table if you don't know that vocabulary, okay? And then the leading coefficient would be this number, negative 2, the coefficient on the term that has the highest degree. What about the next one? Tell me whether you think it's a polynomial or not. And it's not, because we have a negative exponent. That's not allowed. The exponents have to be whole numbers. So it's not a polynomial. Okay, and then think about this one. Is it a polynomial? And it is, because all the exponents, we have a 2, we have a 1, and then this is the constant, so that part doesn't have a variable with it, so we don't really have to check that part. The other parts have whole number exponents, so it is. Go ahead and rewrite it in standard form for me. So think about that for a second. What's the order it has to be written in? Six x squared would come first, but then the minus 3x, because that's, remember, like x to the first, and then again the constant will always come last. Okay, you tell me degree, type, and leading coefficient. So degree, again, is the highest exponent. That's 2. That's how you decide what type it is, okay? Look back at your table again if you need to. If the degree is 2, it's a quadratic. This is going to make a parabola if we graph it. And then the leading coefficient would be the number in front of the x on the term with highest degree. So it's 6, okay? Again, that's helpful to put it in order first, like in standard form, before you try to figure out the leading coefficient. Okay, next thing we're going to look at is review. You've learned direct substitution already. If you have a question that says use direct substitution to evaluate this it's a polynomial when x equals 3, the first thing that you're going to do is rewrite the polynomial. We can write f of 3 if we want. That's just a fancy way to say that we're going to fill in 3 for x. But I'm going to write it out like this. Like I'm just recopying the whole polynomial. But notice what I'm doing, how I'm putting parentheses every time there was an x. And then I'm going to fill in 3. Okay, if it said evaluate when x equals 2, you'd be filling in 2 instead. You're just substituting whatever it wants you to let x equal, okay? And then technically you could punch it all in your calculator. If you're going to do it, make sure you're actually putting these parentheses, or we can, technically it's a PEMDAS problem. So we'll do one of these together, but only one, because you are allowed to just plug it in your calculator. Technically, PEMDAS says do what's in parentheses first, but there's not really anything to do in the parentheses because it's just a number 3. There's nothing to do. Exponents come next. So that means I would do 3 to the 4th and 3 to the 3rd. Go ahead and punch those in your calculator real quick and see what you get. 3 to the 4th should be 81, and 3 to the 3rd is 27. Again, guys, you need parentheses. I'm telling you right now, if this was negative, if you don't put the parentheses, you're going to get the wrong answer. It should still be 81, even if that were a negative 3. So we're done with our exponents. We go on and do multiplication, division. So we have 3 sets of that to do. 2 times 81 is 162. Negative 5 times 27 is negative 135. Negative 4 times 3 is negative 12. Now we can finally just go from left to right and do all the addition, subtraction. So 162 minus 135 minus 12 plus 8 should give us 23. Okay. Now, again, I told you can plug this in your calculator, but technically you should show the steps of PEMDAS, and that takes a little while to do, okay? So in Algebra 2, we learn another type of substitution. So keep in mind, the normal way here is called direct substitution, okay? We're going to take the same exact problem and we're going to learn something brand new right now. So I'm warning you, you've never seen this in your life before, okay? It's going to be something called synthetic substitution. So what I want you to do is we're going to take the same exact problem and we're still going to plug in 3 for x. But here's what I want you to do. I want you to write something on your paper that looks like this, kind of like an L almost, drawn long though, okay? So what you're going to do, if you want to take notes at the same time, you're going to put your x value, 3, right here. And then across here, we're going to be putting all the coefficients of the polynomial. So let's go think about the polynomial for a second, okay? I want you to just look at it real quick. We have 2x to the 4th minus 5x to the 3rd. Then it skips x to the 2nd. Do you notice that? Because it goes right to 4x to minus 4x to the 1st. That's actually going to be important. If it skips x to the 2nd, it means the coefficient on it is 0, technically. That's why if there is no x to the 2nd, it means the coefficient is 0. You need to know that. Because when we take the coefficients and write them, you're going to put 2 first, the leading coefficient, then negative 5. Then you have to put 0 since there's no x squared term. Then you put the coefficient on the x to the 1st term, and then you put the constant, okay? So you're just listing out all the coefficients. All right, so then the next thing you're going to do, I'm going to come down here because it's going to kind of give us directions. And by the way, guys, I'll post this slide at the end of the period, so like the notes. So if you want to look back at the definition or the directions here, you'll have that, okay? So look what it's telling us to do. It says just bring the first coefficient down. That's going to be what you're going to do every time when you do this process. Then read the directions. It says multiply that leading coefficient by the x value. So like these two things, you're going to multiply them. 3 times 2 is 6, and you're going to write it right here. Like, see how where the arrow's pointing? Okay, and then look at the directions. Next thing you're going to do is add straight down. Negative 5 plus 6 is 1. Okay, I know this seems a little weird at first, but now you're going to keep doing it. Your new number, 1, you're going to take it times 3 again. 3 times 1, and you're going to write it here. And then you're going to add straight down again. 0 plus 3 is 3. And then you're just going to do it again. The new number, 3, gets multiplied by this again. 3 times 3 is 9. And then you're going to add straight down again. Negative 4 plus 9 is 5. And then you're going to do it one more time. The new number, 5, gets multiplied by 3 again. So you're multiplying by 3 over and over, and then you're going to add straight down one more time. See how I got 23? Look, that's the same thing we got here, because it's another method to do the same problem. And I know this probably isn't very clear to you yet because we've only done one example. But guys, after you do a couple of these, they actually go by super fast. It doesn't seem like it right now because I'm just teaching you how to do it. So we're learning. It's slow right now, but once you get how to do it, it's actually kind of quicker to do it this way than it is to sit here and plug in the 3 and do all of this math, okay? So again, I know it's not very clear yet. We're going to do another example. If the directions said use direct substitution, you would take 2 and fill it in for all the x's, and you'd have to do all that PEMDAS, okay? Synthetic substitution is the new method we're learning. We're going to take 2 and we're going to put it right here, okay? Just like look back at this example again. Remember, it wanted us to fill in 3, so we put 3 right here. And then think what we did after that, right? We took all of the coefficients and we lined them up right here. So that's going to be the next thing that we're going to do. So this time it wants us to plug in 2. So we put 2 right here. And then we're going to take all the coefficients. So first, stop and make sure, are there any missing? Like, is this polynomial in standard form? It goes x to the 4th, x to the 3rd, x to the 2. But then the constant, it skipped x to the 1st, right? That means the coefficient is 0 there. That matters, okay? Because when we write out all the coefficients here, 3, -6, 5, 0, -10. So you're going to do it in that order too, okay? Like that's why the polynomial has to be in standard form first. It already is, but if it wasn't, you would want to rewrite it. So our leading coefficient is 3. Then the next one is -6. Then the next one is 5. Then the next one is 0. And then the next one is -10. Okay? So you write out all your coefficients. What's up, Ava? Because there is no x to the first term, it goes straight from x to the second to the constant. It skips x to the first, which means that the coefficient on it is 0. Because what, guys, what's 0 times anything? 0, right? So if you don't see a number, if it's missing, it's because it's 0. Like we don't write +0, right? That would be silly to have it in there, but we have to understand that it means it's 0 because when you do synthetic substitution, you have to include all the coefficients, even the ones that are 0, okay? So the process, again, the directions that we're learning. If you look back at the last slide, the first thing it says is bring this straight down, the leading coefficient. And then you're going to multiply these. 2 times 3 is 6. You're going to write it right here. Then you're going to add straight down. -6 plus 6 is 0. Then you're going to multiply again. These this time. 2 times 0 is 0. Then you're just going to add straight down again. 5 plus 0 is 5. Then you just keep repeating it. These are going to get multiplied. 2 times 5 is 10. And then you just add straight down. And then you do it again. 2 times 10 is 20. And add straight down. -10 plus 20. 10, that the last number that you write is your answer. So what that means, guys, is if I were to take 2 and fill it in for all the x's and spend all the time doing all the steps of PEMDAS, I would get the same answer. It's a different process to get to the same thing, okay? Let's try to do one more so you have the hang of it. By the way, guys, you're going to have to read your directions carefully on your homework, because if it says use direct substitution, then you're doing what the old method, like you're just filling in 3 for every x and following PEMDAS and doing all that work, okay? If it says use synthetic substitution, you're supposed to be using this new method that we're learning right now, okay? So what's our x value that it wants us to plug in? 2. That number is going to go right here. Next step, we have to write out all the coefficients. So first, let's go through and see if we're missing any. We have x to the third, x to the second, x to the first, and the constant. So we're not missing any this time, okay? So you take your coefficients and you write them out in order. 5, then 3, then -1, then 7. We don't have any zeros this time because there's none missing, okay? Like real quick, if I went to this one, just check x to the fourth, x to the third. There is no x to the second. It skips right from 3 to 1, right? That means that the x to the second, it has a coefficient of 0. If it's not there, okay, you would include it. But this one's easier because we don't have that. There's none missing. Okay, so see if you're getting the process. Step 1, just bring this down. Then you're going to multiply 2 times 5. Then you add 3 plus 10. Then you just keep doing it. 2 times 13. 26. Then you add -1 plus 26 is 25. Again, multiply 2 times 25. 50. And then add. That's your final answer. So again, guys, the thing is, as you get quicker at these, that's actually probably faster than sitting here and filling in 2 and doing all the steps of PEMDAS. After you practice some of these on your homework, you're going to get quick at them.